All right. Hopefully, with your bell ringer, and I think we even kind of talked about this yesterday, it's like feeling a little bit like there's a shift in what we're going to be focusing on. Okay. We spent a lot of time in the first unit going over constructions and like how to actually make lines and angles and that. Now we're going to switch gears a little bit and we're going to talk about some algebra stuff. And how does this algebra idea that you've learned before apply and integrate into geometry? So we're going to kind of talk about that. So in that bell ringer that I gave you, you were solving an equation, basically. You were given a value for the x, you plugged it in, and you solved it. Now, I could have done any value for x. I chose the one I did just because I felt like it. But I could have chosen any x value, and you could go in and like repeatedly plug in and get multiple y values for that. The equation I had on the bell ringer is called a linear equation because it makes a line, and a line is made up of a lot of points. We talked about that in the first unit. Okay, so we're going to talk today about how do we take this idea of like these linear things that are happening in algebra and how do they play into geometry. And one of the things we're going to focus on is something called functions. Functions are huge in math. You saw them last year in algebra. You're going to see them this year. You're going to see them next year when you go to Algebra 2. We talk about functions a lot because they're kind of one of the big like building blocks that we use. So when you have functions, they look a little bit different than like the equation I had on the bell ringer. The bell ringer said, y equals, and then it had our equation. These are written a little bit differently. So even if you just kind of look here, it says like f, and then there's parentheses x. And this one says g, parentheses with the x on the inside. And same down here, except it's an h. Okay, this is called function notation. Why do we write it like this? Why do we start doing these things? Well, think about when we talked about at the very beginning of the year, labels in geometry are important so that you guys know what point I'm talking about, what line I'm talking about, what shape I'm referring to in the figure. The same thing would apply in algebra if I was looking at a bunch of equations. F of x is how I would pronounce that first piece where it's like f with the parentheses. We call that f of x. And the next one would be g of x. And the last one would be h of x. The only thing that's changing is that letter g to h to f. But what that really means, guys, is a fancy way of saying y. So f of x could be replaced with y. So really I could have said y equals 2x squared plus x, which is maybe something that you're more used to seeing, right? You've seen equations like that a lot. I could have written the next one, instead of g of x, I could have said y equals negative 5x plus 1. And same with the last one. That's how I could have written all of them. Okay, but just like when we were talking about labeling in geometry, and so you guys know exactly what I'm talking about, if I have all of my equations that we're working with labeled with y's, it can get confusing quickly if I'm talking about equations and there's not like a quick way to know exactly which one I'm at because I start out by saying y equals every single time. It gets to be a little bit more of like a jumbled mess to figure out which one was she talking about. The second one, the middle one, like which one. Or when you start working with them, and if you had to like start using multiple of them together and you get your y's confused because there's a lot of them in each equation. Okay. So that's why we use this function notation. That's why they're using the f of x, the g of x, the h of x, because they're just trying to say these are a little bit different from each other, and we want you to be able to understand exactly which one you're working with and like cause less confusion. So when you see those, though, I just want you guys to know it's just a label in math. It doesn't mean that this is going to be any harder or different than what you've done before. It's just written differently. So what they give us down here in these charts is it gives you a function. So this could be, y equals 2x squared plus x, but it's written like f of x. And then after it says this, find, and then it's got the f and then followed in parentheses. But instead of having an x in there, they put an actual number in. What that means is this is the value they want you to plug in to your equation. So we're going to take this 4 and we're going to plug it in for the x over here. Now there's more than one x, so you're going to plug it into two different areas. So instead of writing f of x again, I'm going to replace that with my f of 4 because that's what I'm evaluating this at. And I'm going to plug 4 in for my x's. Just like on our bell ringer, let's make sure we're using parentheses so that I don't accidentally write 24 squared. And again, you can overuse the parentheses like that and put it around everything that you plug in. Some of you will get to the point where maybe you don't need the parentheses around that last 4 because you just know you're plugging it in. But if you need to just put parentheses in all the time and then start to clean them up later, that's fine. So now you're going to use your order of operations, okay? Your PEMDAS stuff, parentheses, exponents, multiplication, division, addition, and subtraction so that you know the proper way to solve this. First thing is we do have some parentheses here because of plugging in, but there's really no operations happening on the inside of those parentheses. So now we look for exponents. I see 4 squared, so let's start there. What is 4 squared? 16. So we have 2 times 16 plus 4. Next would be the multiplication. What's 2 times 16? Good. 32 plus 4 is 36. Great job. So you can see it's just still using algebra, guys. You're still just plugging things in. It just is written a little bit differently. They're using that function notation. So I would like you guys, I'm going to give you a couple minutes. I want you to try to do 2 and 3. Once you have answers for both, why don't you just do a real quick check with the person sitting next to you or behind you or in front of you to see if you guys got the same 2 numbers.
I got 56.
Okay, so if we go to number 2, you should have been plugging in 11 here for the x. So g evaluated at 11. There's a negative 5 there times 11 plus 1. Okay, what's negative 5 times 11? Good, and then plus 1. Good. Watch your signs. Okay, especially if they start to get really complicated and there's negatives and there's subtraction signs and all that stuff, just be extra careful with those things. Okay, now 3, they gave you a fraction. I know how much students love fractions. Okay, so we're evaluating at 5. So we have negative 2/5. Okay, and then in for my x is a 5. What did this come out to be? Good, negative 2. Some of you might have noticed like there's a 5 here, and if you think about 5 over 1 as a fraction, these 5s reduce. They just cancel each other off. And then you're just left with negative 2. So really not all that bad. I know it was a fraction, and a lot of times students see fractions and they think it's going to be really hard because they hate fractions. That one wasn't so terrible. All right, so I have a follow-up question here. In these examples above, each function has what we call an output and an input. What do you guys think you were given, and what do you think you had to find? So do you think, Parker, that is the input or the output? The input, because you were... Yeah, you're putting it in for x. So doesn't that make sense? If you're putting something in, it should be called the input. And your answer is what you got out of it. So that's why it would be called the output. Good, so let's just write that down. We were given the input, okay, which I'm going to just call x because, again, x is just a variable. It could be any letter. Instead of saying negative 5x plus 1, they could have said negative 5b plus 1. So x is something that can change. But you were given the input, and you had to find, or you found, the output, which we call that f of x, or g of x, h of x, whatever they want to use for that function notation. Okay, so now if you guys look at the next couple of examples underneath it, 4, 5, and 6, just kind of compare 1, 2, 3 to 4, 5, and 6 down here. What is changing? Logan.
finding the input instead of the output.
How do you know that?
Because they give you the output already, and they don't give you an input.
Okay, so he's saying that we're finding the input because they're giving you the output. How were these written differently so that you knew that?
Is instead of being f of a number, it's f of x equals that number. So
Yeah, do you guys see what he's talking about here?
Yeah.
Specifically, this piece is what's different. You know, the equation looks the same because we just dealt with 3 examples like that. But he's saying instead of putting that negative 29 in parentheses that follows like the f, it says f of x equals that negative 29. Good. So that's how you got to be able to look at these problems when you're on your own, especially if they start to mix them up. You got to be able to know, what are they giving me? What are they providing me with? So I agree. They're giving you the output here. We want to find the input. How are we going to do that, Keegan?
You put an equal sign in between them and then solve for x.
Yeah, so you're going to take the equation. In this case, it's 8x minus 5. You're going to set it equal to the output, which they're saying is negative 29. Because we know the equation, when we evaluated it at some point, gave us an answer of negative 29. We just have to figure out what did they plug in. So now you're just, again, using your algebra skills from last year, guys, to solve this equation. What are you going to do first? Good. Make sure we always add or subtract terms first before we multiply or divide. So we add 5. What's a negative 29 plus 5? Good. And then what do we do? Good. And we get, good, x equals negative 3. Okay, so now that you kind of see the difference here, just like up above, I want you guys to try 5 and 6. If you have answers, go ahead and do what we did before. Compare with someone next to you. Okay, let's talk about these. Number 5, I got it set up here. How did you guys solve this? Add 3 first. And how do we undo a squared?
Square root.
Good, square root it. Okay, just like multiplication and division are opposites, addition and subtraction are opposites. Square rooting is the opposite of squaring something. What is the square root of 16? Ooh, I love that. Positive or negative 4. Now, if you said just 4, that's fine, guys. Okay, because when we square root things, most of the time we think about the positive root. That's called the principal square root. That's the one that we always think about. But technically, there is a negative side to a square root because what's negative 4 times negative 4? Still positive 16. So if you included the plus or minus sign, you get an air high five. You do not have to have the plus or minus. Okay? If you just said 4, that's fine because I'm not going to be super picky about that. I will tell you, though, next year when you guys go to Algebra 2, we are picky about that. We do need to see the plus or minus because you work more with both roots. So if you see a square root, maybe just remind yourself, oh yeah, there's that other root too if you're not going to write out the plus or minus. Okay, 6. How'd you solve this one? Keegan.
Put negative 15 over 1
Okay.
and simplified it.
You simplified it? How? How do we get rid of the 1/3 over here? Ben?
like bring the 3 up top and make it negative, and then divide -3 by -2.
Okay, I agree with you slightly. You don't want to take the 3 divided by -15 because we want to.
Like -15.
Yes. Now, okay, so I think what you're saying is something like this, maybe?
Yeah,
Kind of. Maybe you didn't have it over 1. Maybe you're just
Yeah.
thinking about the 3. Yeah. Do you have something else?
Multiply by 3 at first.
Multiply by 3 at first? Okay, so let me just kind of get rid of these things. So yours looks maybe like this.
Yeah, because then it gets rid of the 3 on the bottom.
Yeah, so when you guys work with fractions, especially when you're multiplying and dividing, I don't want you to just divide by that 1/3, okay? Because dividing a fraction by a fraction gets confusing and complicated because it's called a complex fraction when you're dividing a fraction by a fraction. I want to try to avoid that, okay? I want to make fractions as easy as possible here. So instead, I'm multiplying by the reciprocal. You're taking that 1/3 and you're really flipping it upside down, which is where the 3 is coming from. Now, if you put 3 over 1, that's fine because that is the true reciprocal. But anytime we have a number over 1, we just write it as the number itself. So I agree. These go away. That gets us our x. And then all you had to do here is take -15 times 3, and you got good, -45. Okay, so this time, what were you given? Output, and we found the input. Is there a quick way that when you guys look at those problems that you would be able to know there's a difference?
Oh, the and sign?
The what sign?
Like the and?
Oh, the and where it says kind of and instead of up above it just had commas, right?
Yeah.
Yep, that would be one. That's like one way you could see that. Okay.
If it gives you the values of G or F of a number, or if it gives you equals a number.
Right. So kind of like that placement of the number. Is it in the parentheses or was it outside of the parentheses? That would be another way for you to tell the difference. Okay. Again, that's kind of something that you have to develop on your own. You know, when I look at them, there's things that I'm looking for to know which is which. You guys have to kind of get used to that, especially if we start to mix these kind of problems together. You're going to have to be able to recognize, okay, I'm plugging this one in versus I'm setting them equal to each other. Okay. All right. So let's kind of do a little bit of that mixing up here. We're using the same equation for all 3 down here. They want you to use this function f of x equals x plus 5. So we're using that for all 3. And they want you to determine either the missing input or the missing output. So for number 7, what are we going to do? Plug in -4 for x because they're giving you the input. So you're going to plug it in. So -4 plus 5 is? Good, 1. And that's your output. What would you do for number 8? Keegan.
Do x plus 5 equals -1?
Yeah, x plus 5 equals -1 because they gave you the output this time. And then you solve for x, and what are you going to get? Good, -6. And how about 9? 2.5 plus 5 because you plug it in. And you get 7.5, 7.5. Good. Questions on that front side? Anybody? We feeling okay? Okay, so that's a lot of algebra, but we're not in algebra anymore. Okay, we're in geometry. So let's talk about how does this relate to geometry? What do functions look like now? Because while the function notation that we saw is relevant, okay, and we're still going to see that show up in geometry, we're going to kind of shift now to how does this apply if I'm actually looking at physical shapes? If I'm looking at triangles, if I'm looking at line segments, what do I need to start looking for in order to evaluate a function in the geometric sense? So in geometry, we have a similar input-output process, okay, just like we did on the functions. Instead of thinking about just strictly numbers on the coordinate plane, these numbers on the coordinate plane that you're working with are applying to potential shapes. So in the future, we'll start talking about triangles and quadrilaterals and kind of what's happening to them on a graph. And we call those transformations, okay? And so in the future, we'll talk about the like specific types of transformations and the different ways that we can apply these to shapes. But right now, we're going to just talk about something called a coordinate rule. Coordinate rules are used in geometry as functions, and they tell you what is happening to your shape. What's being happening to like the x and the y value in order to move the shape around on the coordinate plane. So when we look at something like down here, where it's got kind of this written out, we still have an input and we have an output. Your input is going to be the coordinate that you're working with. So it's going to be points from the shape when we graphed it. So remember, coordinates are always written with an x and a y. The output is going to be what did they do to the numbers to make them change? How did they get this triangle that was sitting here originally moved so that it was over here? Okay, so the output, it looks kind of like the algebraic things that we saw. You're going to be doing stuff to your x and y. So like this one says x plus 3 and y minus 6. Okay, that's two different operations that we're performing. Now, does it always have to be like adding and subtracting? No. Sometimes they're going to have you multiply, divide the coordinates. Maybe they'll have you square the coordinate. So the rule can kind of change, and it can be any combination of those operations if they really wanted it to be. Now, how we refer to this in geometry, instead of calling it input-output, is we have something called the pre-image and the image. Okay, and those are going to be words that we hear a lot going forward from today. The pre-image is where you started. Okay, it's what the shape was before we started doing a whole bunch of stuff to it. The image is what you get after you do all the things. Okay, so if I did a transformation that caused my shape to switch positions, maybe it turned around, it's upside down now, that's going to be all reflected inside of this. The original shape is called your pre-image, your new shape is called your image. If we think about how this would like be spoken out loud, if I was talking about this and I had to read this to you guys and not have to describe all the symbols that you see, this is what I would say. Coordinate rule T maps all points x, y, that's my coordinate, to x plus 3 and y minus 6. So that's just telling me what are they doing to my x and y's on my picture here. Because there could be a lot of them. There could be more than just one point that we're doing this to. So let's think about what this does really on the graph. Like if I were to like plot this point 4, 2 that they're giving me here, let's talk about what happens. So when it says x plus 3, guys, the plus 3 is x movement. X is on your horizontal axis, right? So you can either go left or right on your x-axis. If you go left, do you think that's a positive or a negative movement on the x? Negative, because you're going towards the negative numbers. If you go right, then it would be positive. So up here where the rule says x plus 3, that means that you're going to move right 3. Okay, so x is horizontal movement. What direction is y? Up and down. Okay, that's your vertical movement. Up would be positive, down would be negative. So when they say y minus 6, what direction are they moving? Down 6. Okay, that's what's really going on the graph. But algebraically, we don't need to actually plot the points and then count 1, 2, 3, 1, 2, 3, 4, 5, 6, like actually do the movements. We can instead plug those points into the rule and find the new point and then just go and graph that. So if I want to put this in, I'm going to kind of skip down here. This new point is labeled A prime. We talked about that. If you guys take 4 and you plug it into the rule, what's 4 plus 3? 7. And what's 2 minus 6? Negative 4. Okay, and that's called your image. Okay, and up above, I'm going to fill these in now. The pre-image is just like the input. The image is just like the output. So same idea, different language that we're going to be using in geometry. Instead of saying input, output, I'm going to be talking about pre-image and image. So let's practice here. Let's use coordinate rules, And like I said, these coordinate rules are going to start to get a little bit more complicated than just adding and subtracting. They're going to maybe have you do multiplying and add and subtract and do a combination. So here's my new rule. 3x minus 1, that's just for the x portion. And then the 5y, that's after the comma. So that's a new rule only for your y. Okay, my coordinate here, A, is at 3, 2. And just like what we did on the other side of the page, we're going to plug this into our rule. So I'm going to plug 3 into the 3x minus 1. So I'm going to take 3 times 3 minus 1. That's just for the x portion. What is 3 times 3 minus 1?
8.
8. So that's going to be my new coordinate. Okay, and notice how that's being put in the blank there next to that A prime, because I'm finding the new image. Okay, what am I going to do to find my y?
5 times 2.
Yeah, 5 times the y value, which is a 2. And 5 times 2 is 10. So there's my new value. Okay, why don't you guys do 11? Different rule up here, so just take note. This is a different rule. New coordinate. Go ahead and compare with your neighbor. See if you guys got the same coordinate.
Yeah.
What'd you guys all get?
6.
Negative 5, comma, positive 6?
Yeah.
Everyone agrees? Okay. What's different about 12 and 13?
You have to find the
You have to find the pre-image point. Okay? They're giving you the image point. They're giving you where we ended. So think about how we did that on the other page, on the other side. We were setting the equations equal to the output. So in this case, what am I going to set the 5x plus 3 equal to? To what? 13. Why 13? It's the x output. Okay? It's the x portion of the image. So again, just like when we were plugging the x into the x portion of the rule, you have to still keep those together when you're setting them equal to each other. Okay? How are you guys going to solve that? So we have 5x equals 10. Then what? And we get 2. Okay, and again, notice how they've also switched it. We're not looking for the prime one. We're looking for the original. Okay, how do we do that for the y? Don't plug in negative 7 for y. They're giving you the output this time. So you take 7y and you set it equal to negative 7. And then what do we do?
Divide by.
Divide by 7 and we get negative 1. Good. Again, these are slightly different from each other, but if you just kind of, I'm going to zoom out. If you look, those top two, you were looking for the prime, okay? And you were given the original. This one, they're flipping it on you. Okay, so let's do this last one. How are we going to set up for the x? Logan?
What I did was I set up, it was negative 4 minus 7.
Well, how would you just set it up as an
Oh.
algebraic equation right now? Because I agree that's what you're going to do, but how'd you get there?
Sorry.
You're going to set x plus 7 equal to negative 4, right?
Yep.
Because then that's how you said, okay, now I'm going to subtract the 7. And what did you get?
I got negative 1.
Good. Now the other one has a fraction. Okay, you have 2/3 y is equal to 4. How do you guys want to handle that? Parker?
multiply by 3 on
Well,
both sides.
Okay. So I have 2y equals 12.
And divide by 2.
And you get
Y equals 6.
good 6. Okay. Questions?